It's my fault. All right. My stream. Okay, let's see. Yeah, yeah. I think somebody can. I'll make someone co-host. I guess. I don't know why you guys are not co-hosts.
Go to the participant to the security.
Okay.
Enable waiting room.
Okay, that's easier. Okay, go ahead. But I should still make some people co-hosts.
Yeah.
Okay. It's working. Okay, good. Oh, what is this? Yeah, it's kind of like a mess. Stop. Okay, let's. Okay. All right, let's get started. This is our second to last, our penultimate lecture. So we're going to have one more tomorrow on virtual memory, but today we'll cover prefetching. There are many exciting topics in this course, but prefetching is perhaps one of the most impactful topics that you can study today in entire systems. Certainly, we know that memory hierarchy is a big bottleneck, and prefetching is a very good way of getting performance out of the memory hierarchy at the expense of potentially some things. So we will discuss prefetching. I mean, this entire course, I worked on many parts of the course in my life, hands-on actually, in many topics. But probably I worked on prefetching the most, implementing different types of prefetchers in real processors, as well as different types of prefetchers in research. So I think it's quite exciting. And I still think there's a lot more to do in this area. This is an area that people need to focus on even more. Okay, even in data-centric systems, if you put processing into the memory, you still may need to do prefetching. Okay, but before we jump into prefetching, let me talk about, well, I don't think I have the slide over here, but you have an extra credit assignment with Amdahl's law. How many people have done it? Okay, that's great. Did you enjoy the paper? Okay, it's short and the terminology is a bit different from today, but it gets across the point, right? Hopefully. Okay, so that's your extra credit reading. But these are the readings, I think, in full about memory hierarchy, caches, prefetching, virtual memory. Tomorrow, I'll give you some virtual memory readings. If you have time today, we will start virtual memory, but we will see it. My guess is it's going to be unlikely because I think there's a lot to cover in prefetching. Okay, so remember we were discussing the memory hierarchy, and this is our memory hierarchy example. We went through it and we discussed a lot of management issues in the caches. But one issue is, can you predict the data that you're going to access and bring it into the cache level that you need? And that's the idea of prefetching, basically, preloading data to even the register file potentially. And of course, now design space gets even more complicated because where do you prefetch the data? Where do you place the prefetcher? Is it between L1 and L2, L2 and L3, L3 and the main memory? Is it at the main memory? So there are a lot of interesting issues over here. If you prefetch it if you place the prefetcher everywhere, then the question becomes how do you coordinate between them? And how does it interact with software? Also becomes a very interesting issue. So and this is our memory hierarchy. So you can do prefetching across many different levels. And this is a picture that we looked at very early on, if you remember. But this is this is extending the memory hierarchy. So new memory technologies, DRAM, existing memory technologies may be extended with other memory technologies like phase change memory. And that is an extension of the memory hierarchy. Now, how do you manage this memory hierarchy becomes a slip problem. These are things that we discussed, but we didn't go into the details of in the last lecture. And prefetching is one way of helping the management of the memory hierarchy, because you can see that these are different technologies that are part of your main memory, and they have different characteristics over here, as you can see. Again, we've discussed this as DRAM versus PCM, but this is something that's happening in real systems. You have hierarchy levels that look like this. And even in main memory, if you look at main memory, it looks like a hierarchy, basically, right? Because memory is so important, we need levels and levels of hierarchy. And then we also discussed that even if you look at main memory, there's also an external part of main memory that may reside in some other node, remote node. And the latencies to that remote node can be at the microsecond levels, right? If it's microseconds and the processor needs data at the nanosecond level, how do you actually get the data from a remote memory node to the processor such that the processor doesn't stall becomes a problem. And again, prefetching becomes important in these scenarios as well. So you can fetch data from a remote server into the server. And this is actually a very general, broad topic, right? We're talking about prefetching into the memory hierarchy of a processor, but prefetching is used in distributed software that you may have in your data centers, for example. If this thread that's running on this server needs some data, it may prefetch it from some other server potentially. And we gave the example of a web browser, for example, right? Last time, we said that you can have a web cache inside your software that caches the pages that you've accessed. That web browser can also be aggressive and can prefetch the pages you have not accessed yet. So you access a page, and there are a bunch of links on that page, and the web browser says, oh, I think this user is going to click on these links, so let me prefetch them before the user clicks on those links. That way you can actually tolerate the internet latency, and a lot of web browsers can actually do that, potentially. Okay, so I'll give you more examples, but this is again to jog your memory. We're talking about these huge memory and cache hierarchies. And what is shown over here is the caches, but what is not shown is really the prefetchers. So there are prefetchers in all of these systems, and there are multiple different prefetchers, and we're going to see some examples of them. Okay, so we were talking about, I'm still covering some basic slides, but I'm giving you the perspective of prefetching in these basic slides that we covered last time. Remember, to improve cache performance, we had three fundamental goals: reducing the miss rate, reducing the miss latency or cost, reducing the hit latency or hit cost. And all of these together affect performance, and you know that very well by now. Prefetching actually can reduce the miss rate by bringing the block earlier into the cache before the processor needs it. As a result, you don't get a miss on the block that you need because the prefetcher was smart enough to bring it into the cache before the processor or the program needed it. If it cannot reduce the miss rate, it can reduce the miss latency or miss cost, because the prefetcher starts a prefetch from the main memory, for example, and when the processor needs that data, the request is still in transit, but it didn't completely make its way into the cache yet. But you reduce the latency from the processor's perspective. So prefetching can be actually very beneficial. Hit latency is a tough one, so it's not going to be, prefetching may not help that, although you may imagine some other ways of handling it. Okay, so these are some things that we discussed last time. We're going to discuss prefetching as a way of improving cache performance or memory hierarchy performance in general by reducing the miss rate and reducing the miss latency and cost. But just to jog your memory, last time we talked about, for example, software methods for reducing the software approaches for reducing the miss rate and miss latency and cost, and also hardware approaches for better replacement and insertion policies. Remember the cost of a replacement in caches. Okay, and we said that there's a lot more on the memory hierarchy, and you can look at them. And we had actually an optional lecture on multi-core issues in caching. How many people watched the optional lecture? I'm curious. There are some people. Okay, that's good. I mean, you're not going to be responsible for anything in the exam, but it's good to know the issues that multiprocessors have, because they exacerbate a lot of the issues that we have in memory hierarchy. Memory hierarchy is a problem in a single processor. It becomes a much bigger problem when many threads are accessing the memory hierarchy. And today, all systems have many threads accessing the memory hierarchy. We have multi-threading inside a core. We have multiple processors. inside a core. As a result, caching becomes a much bigger problem. So if you watch that optional lecture, there are some things that we cover, like should the cache be private to the core? Should the cache be shared between the cores? And that's one fundamental decision. And clearly, this is dynamic versus static partitioning between the cores. You can also think of it that way. And L2 cache is an example over here, as you can see. Should the cache be partitioned across the cores, or should the cache be shared across the cores? And there are a lot of issues that you run into if you start sharing. And there's underutilization that you may run into if you actually do partitioning. Okay, I will not go into this more, except to say that regardless of whether the cache is private or shared, prefetching may bring data into the cache, and issues may get exacerbated. So for example, if you prefetch data into a shared cache from the memory controller, based on the access pattern that you predict by one core, you may actually be kicking out data that belongs to some other core, right? That is brought into the cache by some other core. So you can actually create interference inside your cache because of prefetching. So prefetching can be good, but also it can be bad. Keep that in mind. And that's a trade-off in the end. And system designers try to make the prefetchers as good as possible while avoiding the negative effects of prefetching. And we will talk about those. And again, there's a lot of issues in multi-core cache and prefetcher management you can find online. Okay, I will not go into this. You can find this information also in the optional lecture. But I will mention one more thing, cache coherence. Since you've seen this in parallel programming, I will not go into detail. There's a lot here also. And the basic problem with cache coherence is whenever you have caches, you may have multiple copies of the same data, right? And let's take a look at this example. If multiple processors cache the same block, and if one of them writes to it, how do you ensure that another one gets the updated copy, right? Or doesn't read? At least it doesn't read the old copy. Eventually, it gets the updated copy. So let's take a look at this issue. So you have this processor loading into R2 some value, and the value is 1000. It's consistent with memory. And then this processor also loads that value into its private cache. We're assuming these are private caches right now to the cache, to the processors. And then this processor does something to that value and updates it. So the memory location is updated in the cache of this processor, but not updated in the cache of this processor. Now, the intuitive way of thinking says that the new value of X is 2000. So everybody that reads reads X at this point should read 2000, right? That's the basic notion of happen before relationship, right? You need to obey the happen before relationship. And a lot of synchronization mechanisms actually are built on that happen before relationship. So if this processor actually accesses X at this point, it should not load 1000, but 1000 is cache. And this cache is, if this cache is invisible to other processors, this processor may load a wrong value. And if you don't provide some support such that this processor doesn't load the wrong value, you may actually get wrong results in your program, because clearly these two processors are sharing some data, right? This could actually be a synchronization variable. They may be synchronizing on some particular code that needs to be executed by only one of them, for example. And if this processor sees that this is 1000, it may actually do something semantically wrong from the perspective of the program. So the question is, how do you ensure that this processor, you keep the caches consistent or coherent, in other words? And there's a lot of interesting issues over here. Is this the software's job? Is this the hardware's job? It turns out, we're going to talk about virtual memory soon. With virtual memory mechanisms, you can provide this sort of coherence at a very coarse granularity, at page-based granularity, we will see. But it's very, very costly, very high overhead. So what existing processors implement is they use hardware-based cache coherence. And they basically have mechanisms where they keep track of the modifications to cache block. And if one processor modifies a cache block, other processors are made aware of it. Other caches are made aware of it. And other caches have a signal, for example, saying this cache block at address X got updated. So invalidate your own copy, for example. So that's an invalidation-based protocol. Okay? And there are many, many protocols that we will not cover in this course. So one very simple coherence scheme that is not implemented in existing process because it's too simple. There's a lot of downsides to it. But the basic idea is to have all caches somehow observe each other's write and read operations. And if a processor writes to a block, all others invalidate the block. This ensures that no one gets the, let's say, old copy of a cache block that someone wrote. So it preserves our invariant and it holds the happened before relationship in a distributed system like this, right? And this is a distributed system, basically, if you look at it. There are distributed caches across the system. They could be on chip, of course. Okay, so if you do this, this is a very, very simple protocol, basically. I will not go through the details of it, but you can see that each cache block can be in a valid state or invalid state. And it observes what this processor does to the cache block and what other processors does to the cache block. This processor writes or reads, or and then you send a signal bus write to everyone so that they see it. But if you, for example, if you have a cache block in your cache as valid, and if you see a bus write to this cache block, you turn that cache block into invalid, because this bus write signals that somebody is writing to this cache block, and everybody else, other than the processor who's not writing, should invalidate the cache block. And this is a very simple protocol. It requires only valid, invalid bits, which already exists, basically, to 1 bit. And this is one reason why a cache block can become invalidated, for example, in a multiprocessor system. Okay? Okay, and there, of course, whenever you're dealing with issues like this, you need to make sure that your assumptions are correct. This works based on some assumptions, write to, no write, allocate. But again, I will not go into details of the process. Existing processors implement much more sophisticated processors because this turns out to be very bandwidth intensive. For example, if a processor keeps writing to a cache block, everybody else keeps invalidating the cache block. So there are a lot of invalidation signals that take place in the system. So existing processors, existing systems have mechanisms where they say, this processor is writing to this cache block, and it is the only one who has the copy of the cache block. So you don't need to notify anyone else. So if you know that information in a cache, then you can basically get rid of a lot of invalidations in the system. And that's the basic idea of the MESI cache coherence protocol. MESI, you may have heard of it. It's basically a 4-state protocol. It kind of looks like this. Essentially, if you take the advanced architecture course, you will see how it operates. And it was implemented first, well, at least commercially successful in Pentium Pro again. Pentium Pro actually had a lot of ideas that went into it that made it very commercially successful. And this cache coherence protocol was one of them. And you can see that it's a more sophisticated protocol. But the key idea is to reduce the invalidation traffic and the bandwidth that happens between the processors. Okay, so one more thing related to this is, this is an invalidation-based protocol, right? But there are also update-based protocols. If you go back to this nice picture, we said that this processor should not load 1000, but maybe one design choice is whenever this processor writes 2000, it also sends the copy of the cache block to this processor or everybody. And you update the cache block to become 2000 as opposed to invalidating it. So there are two fundamental ways of handling cache coherence, update-based versus invalidation-based. And there are interesting trade-offs related to it, which we will not get into again in this course. But if you're interested, there's a lot more in this. And this is, people have extended this cache coherence state machine by adding more and more optimizations. Of course, adding more optimizations makes the protocol more efficient, but there's more states that you need to maintain. So complexity also increases in the systems. So that's a very fundamental trade-off again. Okay, and then there's another issue. So okay, before we go into that issue, now if you start prefetching cache blocks to your own cache, you need to also take this into account, right? Where do you get the data? Where do you get the most up-to-date copy into your cache? This becomes also important. You don't want to get stale values. So prefetching and cache coherence protocols interact with each other as well. You may actually prefetch some data that's going to be invalidated, for example. That is a useless prefetch at that point. Okay, there's also another issue called memory ordering and consistency. This is also very critical for synchronizing between different processors. Have you seen these issues like memory consistency in parallel programming? Okay, so you've seen sequential consistency, for example, and you've seen how hardware provides that? Maybe not. So-so, okay, people are saying so-so. Yeah, how to design the hardware that provides it is the subject of a more advanced course, I should say. It's a very fascinating topic. And there are interactions between coherency and consistency, like cache coherence and consistency, which we will not get into, unfortunately. It's interesting, but no time. And prefetching also interacts with this as well. But you can take a look at, let's say, either take the future course or take a look at online lectures if you would like to learn more about how consistency and coherence interact. So I think maybe I'll say one thing over here. Cache coherence is about a single cache block, right? You have a single cache block, different processors update it. You're trying to ensure that nobody gets the wrong data. Whereas unfortunately, it's called consistency. I like calling it memory ordering. But memory ordering is all about the global order of accesses that different processors see. So this is not about the single cache block, but this is really the global ordering of all accesses that you see. And if all processors see the same global order, that's good because they can infer this happened before relationship and ensure that basically if that order, if that happened before relationship is maintained, you can synchronize as a programmer, you can semantically synchronize between different processors in a nice way. But if your hardware somehow violates that happened before relationship by exposing a different global order to one processor than to another processor, now you run into synchronization issues. And that violates the consistency essentially. So your hardware needs to be designed such that you don't violate the perception of the same global order across different processors. Okay, if you did not understand any of that, that's okay. But if you understood it, then probably you're dealing with a lot of synchronization potential. Okay, so let's jump into prefetching, because prefetching, so the reason I covered the earlier parts in a little bit more detail than I normally do is because prefetching actually interacts with all of those issues also. So on top of all of those issues, now we're going to complicate the system to add prefetching. System will try to automatically figure out what data will be needed by what processor and prefetch it into the caches or some other place, because it doesn't have to be the caches as well, right? But if you don't prefetch into caches, you run into the coherence problem again, right? If you have a separate buffer that you decide you're going to prefetch the data, where does the processor get the data from, right? It looks at the L1 cache, and then it looks at the separate buffer, and these two need to be kept coherent also, right? So just now we're just talking about prefetching and coherence, as you can see. Okay, so the idea, I think it's already clear to everyone that the idea is to fetch the data before it's needed by the program. And again, this is a very fundamental idea. It's not just about hardware. It's not just about software. It's really about systems, right? For example, the operating systems have sophisticated prefetchers. Windows, for example, incorporated prefetchers into it more than a decade ago. Actually, now it's like 15 years ago or more. And the idea was to predict which program the user is going to use at a particular point in time and preload the program from the disk to the main memory so that the program can be launched much faster, right? So that's a method of prefetching, as you can see. And that's a system level prefetching mechanism. And they actually used interesting machine learning algorithms at the time to decide which program is going to be used by which user at what time of the day. Okay, so basically to ensure that something happens faster from the perspective of the user or the programmer, we're going to preload the data somewhere. In this particular case, we're going to talk about the memory hierarchy of a processor, right? And the reason we would like to do this is memory latency is high. If we can prefetch accurately and early enough, we can reduce or even eliminate that latency. Right? If we get rid of memory latency such that everything is an L1 cache hit, that's great. And remember, that was our goal in the memory hierarchy. We have this memory hierarchy such that hopefully we always get L1 cache hits while getting the huge capacity of the entire memory hierarchy. And prefetching is an integral component. And the big thing in prefetching is it can eliminate compulsory cache misses. Right? No other mechanism can eliminate compulsory cache misses. Yes, large cache blocks can eliminate compulsory cache misses if you think about the perspective of the data you're accessing. But that's a method of prefetching also. As you make your cache blocks larger, you're essentially predicting that your spatial locality is high. So you're really prefetching whatever is around that cache block, right? Whatever is around the data that you're really truly accessing. Okay, so the question becomes, of course, can it eliminate all cache misses, capacity, conflict, coherence? And the answer is very quickly yes, basically. As long as you can prefetch the data, predict what you need, you can eliminate all the cache misses. Okay, of course, this involves predicting which address will be needed in the future, right? And this is critical. If you cannot predict this accurately, then you have a problem. And essentially, the idea works if the programs have predictable misaddress patterns. Of course, the question is, who defines what is a predictable misaddress pattern? And that's where things get a bit interesting and creative. That's where architecture really comes in, because a predictable misaddress pattern, a misaddress pattern that you see may be predictable with one algorithm, but may not be predictable with some other algorithm, right? So basically here, prefetching algorithms to figure out the patterns in the data, in the access patterns becomes very important. Okay, so there's nothing that, as far as I know, that theoretically says this address pattern is not predictable. Because we're going to see some methods that can predict any access pattern. Why? Because what they can do is they can, you have the program, and this you can create a prefetching mechanism that distills the program and creates another thread. And the function of this thread is to execute part of the program. And the sole purpose of that thread is to prefetch data into the caches. Right? So basically, you're doing some work that the program is going to do, but you're doing that early in some other core, for example. And that thread's sole purpose is to predict data, predict addresses, and bring the data early into this main program's caches. So that's, I think, a fascinating idea. You have a main program just for execution, and you have a prefetching program that's much simpler. And if you do that, there's no address pattern that you cannot predict, right? Because you're really executing the program at that point. Of course, you need to synchronize somehow between those two threads. Okay, maybe I'll raise this question quickly and answer, because we've covered this at some point. Does a misprediction prefetching affect correctness? Like if you mispredict an address, you say that I need the data, the predictor says, I need the data at address X, but the processor doesn't need that data at address X. Does that affect your correctness in the program? And some people are not like shaking their heads, and they're correct, basically. It doesn't, right? You just prefetch the data, potentially, and the data comes in and you don't use it. Nobody uses it. Of course, you may prefetch data that you don't have access to. Now we're going to talk about virtual memory next. Virtual memory is going to prevent that. If you try to prefetch some location in memory that you don't have access to, virtual memory is going to say, no, you don't have access to that data, and that prefetch gets dropped, basically. Okay. Yeah, I think I've said this basically. So there's no need for state recovery, in contrast to branch misprediction or value misprediction. So in a sense, it's easier to do, because if you do something wrong, it's not going to affect your correctness. So in general, these mechanisms that don't affect your correctness, speculation mechanisms that don't affect your correctness, are easier to design and reason about, because something you do wrong in the worst case is going to hurt your performance. It's not going to affect your correctness. But this is a speculation mechanism, meaning you're speculatively accessing data, and this could potentially lead to side channels like Meltdown and Spectre that we very briefly talked about in the early lectures. So keep that in mind also. So let's talk about some basics in prefetching. So if you look at modern systems, prefetching is usually done at cache block granularity, because caches are so integrated into the system that we think about memory access in terms of cache block addresses. I access cache block A, and then A+4, and then A+8, and then A+12, A+16. That looks very predictable to me, right? The stride is 4, and a basic stride prefetcher can prefetch that. Basically recognize the pattern in the cache block accesses and try to reduce the miss rate and miss latency by bringing the cache block earlier into the memory hierarchy. And of course, who does this becomes a question. Does the hardware do it? Does the compiler do it? Does the programmer do it? Does the system do it? And system may be cooperatively between hardware, software, and operating system as well. So this is why this is a very rich area of investigation. Okay, let me give you a more concrete example. This is from a paper that we wrote, as you can see, almost 17 years ago. And you can see that this was the memory hierarchy at the time of general purpose processors. They just got extended, clearly. You have an L1, I cache, D cache at the L1 level, and then L2 cache, and then the rest was off chip, basically. A memory controller here that's off chip. At that time, memory controller was off chip. Today, many memory controllers are on the processor chip, actually. So you can see that what's happening here is we added a prefetch request queue and a stream prefetcher. What this prefetcher does is it looks at the requests that are coming into the L2 cache and tries to detect patterns, basically. And if it finds a pattern, it issues a prefetch saying that, oh, I expect, based on the patterns that I've seen so far, the processor is going to access this addresses. And that prefetch gets inserted into the request queue and then goes through the memory system, basically. So essentially, it's very much like a processor request, but it's tagged specially. It's saying that it's a prefetch. Okay, so now there are of course many questions over here. How do you design this hardware to detect? Is this place the right place to put it? Why not put it somewhere else, for example, at the L1 level, looking at the processor accesses? Why not put it at the memory controller? Now, the new existing processors have it everywhere today, and they may need to be coordinated. And then when you generate a prefetch request, you're clearly using the resources in the memory system. So those prefetch requests are now going to contend with accesses coming from the processor's demand request stream. And as a result, you're going to cause contention, both capacity contention in the L2 cache and bandwidth contention. So if your prefetch is wrong, inaccurate, this may actually hurt your performance also. Okay, and this is just one prefetcher. And we're going to see the prefetching algorithms in a little bit, some example prefetching algorithms. Since it's a huge topic, we're not going to be able to cover all the prefetching algorithms. Okay, so if you want to treat prefetching generally, there are four major questions. Well, at least four major questions: what, when, where, and how. Let's talk about these a little bit. So what is essentially what addresses to prefetch? This is really the address prediction algorithm. How do you do the address prediction? And we'll see some examples. When to initiate a prefetch request? Like how do you decide if you prefetch it, if you initiate a prefetch request too early? This may not be used. It may occupy cache space that could be used by other processes, other blocks, right? If it's too late, it may not reduce your miss latency or miss rate. You just need to find the right time, basically, and this is called timeliness, essentially. Where is actually interesting. There are multiple aspects of where. Where do you place the prefetch data? Do you place it in the caches, separate buffer? Which level of the cache? Which way in the cache? How does it interact with the cache management algorithm? And then there's another where. Where do you place the prefetch? Do you place it right close to the processor, L2 cache, L3 cache, memory controller, all over the place? So there are a lot of interesting decisions here that we're not going to go into details of. How is also interesting. Actually, some of these interact with each other. How especially interacts with everything, because how really is about the general philosophy of how you design the prefetcher. How does the prefetcher operate, and who operates it, basically? Is it the software? Is it the hardware? Is it a thread-based prefetcher, like I briefly described, right? Somebody creates a thread that just does prefetching. This is also called execution-based. Is it cooperative, hardware, software together? And there's also hybrid prefetchers that essentially today's systems have many prefetchers that are working together. Sometimes they're synergistic with each other. Sometimes they're stepping on each other's toes, because one of them is prefetching something, the others are going to evict, for example. So there are a lot of dangers also here. So, okay, let's go into some of these questions. So what is interesting, and we're going to cover some algorithms. What addresses do you prefetch? So prefetching useless data clearly wastes resources. And these resources are many in the memory system: memory bandwidth, cache or prefetch buffer space, energy consumption. If you go to memory to prefetch data, you're actually exercising. And if that access that you're doing is useless, you're wasting a lot of energy also, potentially. And all of these resources can be utilized by demand requests or more accurate prefetch requests. So prefetch requests also have potentially different accuracies, right? Some of them may be accurate, some of them are inaccurate. If you can figure that out and drop the inaccurate prefetches that you don't have confidence on, then you can actually save a lot of these resources. And people actually have developed a lot of interesting algorithms to decide what addresses to prefetch. That's why what addresses to prefetch, the algorithm to decide that, is very important. Okay, let's talk about this accuracy a little bit. I'm going to later talk about prefetching performance metrics, but accuracy is an important metric. Accuracy is clearly important. Prefetch accuracy is defined as, out of all the sent prefetches, the prefetches that are sent in the memory hierarchy, how many of them are used by the processor, basically? So it's a basic metric. It's a fraction, as you can see. And the higher, not necessarily the better, because there are other metrics that affect performance of a prefetcher. Accuracy is just one portion of the equation, right? We just talked about timeliness earlier. And then there's something called coverage. What fraction of the misses you cover actually in the entire program? So a prefetcher's performance is really defined by at least 3 metrics. But there are more also, as we will see. But accuracy is one metric that you use to optimize your algorithms for, but not the only metric. But I just want to give you an example. Okay, then another question is, how does this algorithm operate? How do we know what to prefetch, in other words? And as I said, we will cover some algorithms. But you can predict based on past access patterns, as I just described, right? If your access pattern looks like, if at the L2 level, access pattern looks like A plus 4, A plus 8, A plus 12, A plus 16, then your stride is clearly 4. And a very simple stride-based prefetcher can say that my stride is going to be 4, so it can prefetch A plus 20, A plus 24, A plus 28, etc. But the downside is, if it's really aggressive, at some point the processor may stop accessing things in a strided manner, right? Maybe it stops at A plus 20. The prefetcher kept going on. It went up to A plus 64, and a lot of things may be useless, right? Okay, or you can use programmers or compilers' knowledge of data structures, especially in software prefetching or thread-based prefetching, and this is also very interesting. Okay, so basically prefetching algorithms determines what to prefetch, and people are still optimizing these prefetching algorithms and coming up with new ideas. If we get to it at the end of this lecture, I'm going to talk about a method of using reinforcement learning, machine learning, as a way to decide what to prefetch. So that's a prefetching algorithm that's driven by machine learning, for example. And these sort of algorithms, since prefetching is a lot about pattern recognition and pattern detection, machine learning algorithms have a good place in here. Okay, so when? Let's take a look at the when question. This is the second question. And here the question is, when do you initiate a prefetch request? If you prefetch too early, prefetch data might not be used before it's evicted from storage. If you prefetch too late, you may not hide the whole memory latency. Right? So basically, when a data item is prefetched, affect the timeliness of the prefetch. And you have some control on the timeliness. For example, if you have a stride prefetcher, A plus 4, A plus 8, A plus 12, you can say, oh, whenever I see A plus 12, I'm going to basically look ahead and fetch 10 other accesses that I think are going to be strided. And basically, you'll get 10 ahead of the processor if you do that, right? And then whenever the processor generates one access, you go 10 more ahead. Right? This way, you can actually cover the timeliness issue. Because it's an important issue. If the memory access takes 1,000 cycles, 1,000 processor cycles, the processor can quickly generate strided requests that can bottleneck the memory. Right? So you need to really go ahead of the processor. Okay. So basically, prefetcher can be made more timely by making it more aggressive. I just give you an example of making it more aggressive. If you see a strided access pattern, don't just say, I'm going to access the next predicted address. I'm going to access the next predicted 10 addresses, for example. That's one way of making it very aggressive. Try to stay far ahead of the processor's demand access stream, basically. This is hardware. So this is hardware-based thinking. Of course, you could do this in software also in different ways. But one way is moving the prefetch instructions earlier in the code. So you may have a loop that just does prefetching, for example, for another loop. And the sole purpose of the first loop is to prefetch data. The second loop always sits in the cache. That's one possibility. Of course, you need to be careful about how you do it, right? Okay, so that's when. So where, as I said, has a lot of issues. I'm not going to discuss all of the where-related issues, but I'll pick one. Where do you place the hardware prefetcher in the memory hierarchy? In other words, basically, depending on where you place the prefetcher sees different access patterns, right? For example, if you place the prefetcher very close to the processor, it observes the processor's access stream, all of the L1 hits and misses, basically. So it has a complete picture of what the processor is accessing. If you place the prefetcher after the L1 cache, before the L2 cache, the processor doesn't see L1 hits. Because remember, L1 cache filters some of the accesses that hit in it. So now you have a less complete access pattern. As you go further away from the processor, you have an even less complete access pattern. If you're, for example, in the memory controller, you have a prefetcher in the memory controller, it doesn't see any of the accesses made by the processor that hit in the on-chip cache hierarchy. Right? As a result, prediction may be harder if the patterns become more difficult to detect. But the upside is you deal with fewer accesses as you go farther away from the processor, because hopefully your cache hierarchy is at least somewhat beneficial, and there are some hits in your cache hierarchy. As a result, not all of the accesses go to the main memory. Right? Okay, so I already said this, but seeing a more complete access pattern, basically, as you place the prefetcher closer to the processor, you see a more complete access pattern. This could lead to potentially better accuracy and coverage in prefetching. We're going to define especially coverage later. Basically, you can do better. You can design a better prediction algorithm. But the downside is the prefetcher needs to examine more requests and keep up with the processor's access pattern, basically, right? And this may require, because prefetcher is doing potentially sophisticated analyses on the access pattern, it may not keep up very well, right? This is very bandwidth intensive. You may need more ports into the prefetcher, et cetera, especially if you have multiple cores, right? Think about many, many cores going through this prefetcher that tries to observe all of the access patterns. Okay, so basically, you can place the prefetchers anywhere in the memory hierarchy, as you can see over here. If you have a hybrid memory, like we briefly mentioned, there might be a prefetcher that is prefetching from one memory type to another memory. And there might be a prefetcher that's prefetching from remote nodes to the local nodes, as you can see. And existing systems actually have prefetchers everywhere. Okay, let's talk about the how. This is the last question. Basically, how do you do the prefetching? Who does the prefetching? Software, hardware, execution-based, or hybrid? Well, we'll talk about hybrid at the very end of the lecture, hopefully. But software prefetching says ISA, instruction set architecture, provides prefetch instructions, and the programmer or compiler inserts these prefetch instructions. This requires some effort, clearly, at the software level. I will not go into this in a lot of detail. Existing ISAs all have prefetch instructions. Unfortunately, these don't work well enough. They work very well for extremely regular access patterns, but they don't work very well for irregular access patterns. That's why people have developed a lot of hardware prefetchers. And also, there are other issues in software prefetching. Timeliness becomes harder to reason about. For example, if you're a programmer, you may reason about the cache space you have, but timeliness is a totally different issue. When is an access going to come back from memory? That's harder to reason about because you deal with many, many levels of cache hierarchy, and then there may be other programs also executing on the same system, right? Okay, so that's why hardware prefetchers are actually very, very popular everywhere. In this case, basically, you have specialized hardware that monitors the memory accesses, and either it memorizes, finds, and learns different address patterns, basically. It could be strides, it could be different arbitrary patterns, it could be correlations between different addresses. We will see one example from a more recent prefetcher that tries to correlate different addresses and prefetch based on those correlations, for example. And the idea is to generate these prefetch addresses automatically, transparently to the software. Of course, you can imagine software directing hardware as well, software potentially providing some information, but we'll not go into that. And existing systems actually have that information as well. Execution-based prefetchers are completely different. Essentially, you execute a thread, specialized thread, just to prefetch data for the main program, as I mentioned earlier. This thread can be generated by the software programmer or the hardware. So hardware can actually generate this thread as well. In fact, I'm going to show you an idea that I developed during my PhD thesis that talks about how to generate this thread in a very low effort way. Basically, use the main program for prefetching. So we will see that. So these are actually very interesting prefetchers, very powerful prefetchers, because they don't need to necessarily detect patterns. They execute code to prefetch, right? This is not necessarily pattern detection. Okay, so let's take a look at some examples in real systems. So this is x86 prefetch instruction. Basically, this is one version of x86 in the past, an old version. But you can see that there are different types of prefetching, T0, T1, T2. T0 says temporal data, prefetch data into all levels of the cache hierarchy. And implementation, unfortunately, is very microarchitecture dependent. So in Pentium 3 processor, the processor does something. In Pentium 4 and Intel Xeon processor, the processor does something else. Not so great from a programmability perspective, right? But you can see some non-temporal data with respect to all cache levels, prefetch data into non-temporal cache structure and into a location close to the processor, minimizing cache pollution. Basically, don't prefetch data to all cache levels. That's the idea over here. And there are other types of temporalness, let's say, with respect to data that Intel decided to provide at that point in time. But you can see that the specification is very processor dependent, so it's very hard to maintain code with this sort of instructions in general. Even though technically it's not a bad idea, but in implementation, in practice, software prefetching becomes actually very, very difficult. So that's why people actually implement hardware prefetchers, and this is one nice prefetcher from IBM Power 4. The basic idea is employed in many, many systems. But this basically shows you that the processor is doing streaming accesses. For example, in the L1 cache, you have line 0 and line 1. And you expect that the processor is going to access line 1, line 2, line 3, line 2, line 3, line 4, line 5. So you keep bringing data in a streaming manner from the memory hierarchy to the caches, right? And then in L3, you keep the next, I think, how many? 16 lines over here. And then you keep prefetching from memory every line by line. This is called a next line prefetcher or a streaming prefetcher. You always predict that the processor is streaming. Streaming means a stride is 1. Cache block stride is 1, right? And they actually have nice explanation over here. Maybe I will read it. Power 4 systems employ hardware to prefetch data transparently to software into the L1 data cache. When loaded instructions miss sequential cache lines, either ascending or descending, so you could go up in the memory space or down in the memory space, the prefetch engine initiates access to the following cache lines before being referenced by load instructions. In order to ensure that the data will be in the L1 data cache, data is prefetched into the L2 from the L3 and into the L3 from memory. So basically, you need to prefetch enough cache lines such that you can cover the latencies, because the latency between L1 and L2 is short. L2 and L3 is larger. L3 and memory is even larger. So the number of look ahead that you have in terms of how many cache blocks you prefetch in the streaming manner depends on the prefetcher that's at a given memory hierarchy level. And this is clearly beautiful. It works with a particular access pattern where you keep streaming through memory, right? And this is actually not an idea that was introduced by Power 4. This is a beautiful paper that introduces the idea of stream prefetching by Norm Juppy. Interestingly, Norm Juppy later went to Google in 2014 or so, and he was the chief architect of the tensor processing unit at Google. But before that, he used to deal with a lot of memory hierarchy issues. Not that tensor processing unit actually has a lot of memory hierarchy issues also. But he introduced a lot of stream prefetchers, as you can see. One thing I will mention over here is this. This is actually an old paper from 1990. But it basically makes a point. This WAX 11780 is from 1980s. And miss cost of a cache miss is 6 cycles. In terms of instructions, it's 0.6 instructions. He basically does the conversion because of there's an instruction, cycles per instruction also. But Titan, this is the processor that they were designing where they introduced stream prefetchers, had a miss cost of 12 cycles. And the in terms of cycles, 12 cycles. In terms of instructions, it's much higher. And he's projecting over here saying that miss cost will increase to 70 cycles. And in terms of instructions, 140. So today, we're well beyond 70. Today, we're at 500, 600, sometimes at 1,000 cycles, and maybe more. Basically, that's how memory hierarchy became a bigger bottleneck. Over time, processors became much more powerful, whereas memory hierarchy became a bottleneck, essentially. Because we were able to improve computation, just like we discussed in earlier memory lectures. And this is another example that is good to provide. Okay, so let's cover some prefetcher performance metrics before we look into some algorithms. I already mentioned accuracy. Accuracy is what fraction of the prefetches that you send out are used by or demanded by the processor. Coverage is you have some misses in your program. What fraction of them are prefetched by the prefetcher? So of course, if you have 100% coverage, you prefetched everything, right? But that doesn't mean that they're timely. Timeliness means what fraction of the used prefetchers are on time, meaning they hit in the cache by the time the processor needs to access them. There are multiple definitions of timeliness, of course. Timeliness may be binary like this. Does it hit in the cache or does not hit in the cache? That's a very strict definition. It really comes in shades of gray, right? Because if you look at timeliness, you cover some latency. What fraction of the latency is covered is a better definition, potentially. So there are multiple ways of defining this. But these all together affect your prefetcher, the performance that your prefetcher has on the system. Not just these. We're going to talk about the bottom parts also. But even these are hard to optimize. In general, if you come up with a prefetching algorithm, it's very, very, very hard to get all of these at the values that you like. Basically, 100% accuracy, 100% coverage, 100% timeliness. If you're lucky, you get 2 out of 3 and not at 100%. So this is one of those things where you have a multi-objective optimization space and you cannot get all of them. Not easy, basically. That's one of the reasons why people are actually fascinated by this. There are time and space aspects to it. Bandwidth consumption is another issue. Basically, there's some memory bandwidth that's consumed with the prefetcher, divided by without the prefetcher. And this may increase your memory bandwidth, right? Basically, if you send useless prefetches, you're increasing your memory bandwidth. Or useful prefetches too early, you may be increasing your memory bandwidth by kicking out something useful that you need to refetch again, right? Now, the good news is if you have idle bus bandwidth, you can utilize it, but usually memory prefetchers increase your memory bandwidth consumption and requirements. So cache pollution is a bit harder to quantify exactly, but these are extra demand misses that you get because you're prefetching data into the cache, because you're evicting something else that may be useful, right? So you can see that this, again, the optimization problem is actually much broader than these three metrics. Okay, so there are many, many other prefetching issues that I'm not going to cover in this lecture, but we're going to jump into some prefetching algorithms. If you're really interested, there are a bunch of papers that talk about this. This is one paper, for example, that talks about these metrics, especially, and how to try to optimize them by trying to throttle the prefetches, like somehow identify feedback from the system, and based on that feedback, you try to throttle your prefetcher. And this is actually, this idea is implemented in many systems. We will see later a paper from IBM, for example. They do a lot of feedback-directed prefetching in their systems. Okay, now let me see. Okay, let me talk about this, and then we're going to take a break. We're going to look at an algorithm. But basically, if you optimize your prefetcher, you can do really well. This is data from Sun Microsystems, which later became Oracle. This is a very interesting data, basically. They do some sort of prefetching, which we're going to discuss in the next part of the lecture, early part of the lecture. Here, they show the effect of that prefetching. It's called Scott prefetching. We called it run-ahead execution. They actually revised the idea and implemented that in their real systems. And if you look at the Scott prefetching, it always outperforms no prefetching, right? No Scott is no prefetching, or a baseline prefetcher that is not as, let's say, intelligent. But the interesting thing over here is in the x-axis, you see the L2 cache size of the processor, on top of which they're implementing prefetching, and the instructions per cycle. These are real commercial workloads that these people were designing the processors with. So always the prefetcher improves performance. So you can look, for example, if you look at a cache size of 512 kilobytes, which was the standard at the time, you get 40% better performance with prefetching. But you can also use prefetching to eliminate your cache or get higher cache space, get the benefits of a higher cache space. So if you look over here, these 2 points in the performance spectrum are equivalent. Prefetching with on top of a 1 megabyte cache is equivalent to no prefetching with 8 megabytes cache. So instead of increasing your cache size, just devote some resources to intelligent prefetching, and you can save a lot of area, right? Basically, they say they can buy 7 megabytes here. If their performance target is here, they can buy 12 megabytes. So you can see now, you can play a lot of tricks in the memory hierarchy. We don't have to have these huge caches if you have intelligent ways of managing the hierarchy. Okay, so let's take a break. We're going to talk about intelligent ways of managing the hierarchy using prefetching algorithms. So we'll be back 1 or 2 minutes after the bell. Okay, maybe I'll go back. I think that's true. Sorry. I guess I was muted. Okay, so maybe for the benefit of people who are on Zoom, I'll very quickly cover. Maybe they should have said that earlier. Okay, maybe they did say it earlier. So basically, we're covering this scout threading, which is essentially run-ahead execution. And we covered that small instruction windows lead to stalls. You may have a long latency cache miss at the top. It cannot be retired due to precise exceptions. But other instructions in the window can be executed, but they can also not be retired because you retire instructions in program order. As a result, you cannot bring in new instructions that may miss in the caches, right? So you basically keep stalling for instructions that keep missing in the caches because you have a small window that cannot tolerate the latency of the miss, hundreds of cycles. You really need to be able to bring in many more instructions into the processor to tolerate hundreds of cycles latency. Okay, and we said that earlier also, we said that long latency cache misses are responsible for most full window stalls. This is a study that we did with Intel, as I mentioned, across all of their workloads. We found out that most of the time the processor is waiting for L2 cache misses, stalling for L2 cache misses. Now, if you increase the window size to 2048 entries unrealistically, especially at that time, you gain performance, as you can see, on average more than 30%, which is pretty good actually on average across hundreds of workloads. But still you stall. Basically, L2 misses are so costly that you keep stalling. So clearly, out-of-order execution requires large instruction windows to tolerate main memory latencies that we're experiencing today. And you got an example of what it used to be, right, with the VAX 11780 and Titan processor in Norm Juppy's paper. And as main memory latency increases, the instruction window size should also increase to fully tolerate that memory latency. And unfortunately, as we discussed in the out-of-order execution lectures, building this large instruction window is very challenging, especially if you would like to achieve three things at the same time: low power or energy, short cycle time, high frequency, and low design and verification complexity. So if you build an instruction window larger and larger, which is happening today, it comes at the cost of all of these. People are doing it, but that doesn't mean that it's not coming at a cost. Basically, as we discussed in out-of-order execution lectures, you have this huge tag matching logic, right? Load store buffers, reservation stations. They all add to the power consumption. Wake up and select logic, register file, bypassing the data, forwarding the data across those many different execution units. They all add to the energy as well as the short cycle time. It's very difficult to have a short cycle time with very large register files, for example. And again, if you try to fix these issues, your design and verification complexity increases. You could actually have algorithms to make these much more efficient, but verification complexity increases in the end. Okay, so let's talk about the idea that we developed to actually overcome this, let's say, at the time, or at least a part of it. And that's the idea of run-ahead execution. This is a technique to obtain the memory level parallels and benefits of a large instruction window. And when the oldest instruction is a long latency cache miss, the processor checkpoints the architectural state, the register file and the program counter, and enters a special mode. We'll call it run-ahead mode. This is pure speculation at that point. In this run-ahead mode, the processor speculatively pre-executes the instruction. The sole purpose is prefetching. It keeps executing the instructions just as it would, except the purpose is to generate prefetches, and it ignores data that it doesn't have available. Meaning, if an instruction missed in the cache, too bad. That data is not available. I'm going to forget it, and I'm going to forget everything that's dependent on it. My purpose in this mode is to execute instructions that are independent, and hopefully some of them will generate cache misses. I'm going to start the execution of those cache misses so that they can be serviced in parallel with the cache miss that caused the processor's entry into that mode. Okay? And when the original miss that caused entry into that mode returns, the processor restores a checkpoint, architectural checkpoint. That's the register file and the program counter and whatever architectural registers you may need, flushes the pipeline, and resumes normal execution from the load that missed that caused entry into this mode. Basically, architecturally, nothing has happened. But microarchitecturally, you hopefully prefetched a lot of data into the caches. That's the idea. So instead of stalling, you prefetch data into the caches. So let's take a look at it pictorially. Ideally, you would like perfect caches, right? You compute, loads come, you never stall. Of course, we're not there. With small instruction windows, the processor computes. You get a long latency cache miss. The processor can tolerate some of that because it is an instruction window. But once the instruction window becomes full, the processor stalls until that miss completes. Once that miss completes, the processor computes. And it's nice until it gets another cache miss, after which the same thing happens, basically. So that's why you have these profiles of programs that show most of the time the processor is stalling, because this is what's happening in real life in real processors. And the idea of run ahead says, instead of this red stall, why don't we do some useful work by prefetching data into the caches? That's the idea. You compute, the processor computes, and it gets a long latency cache miss. And at that point, after some point, that long latency cache miss becomes the oldest instruction, so that you can checkpoint the state nicely. And the processor enters a special mode where it speculatively executes instructions and drops instructions that are dependent on L2 cache misses, or cache misses in general. And it reaches an independent load that misses in the cache, and the processor starts that cache miss much earlier than it would if it had stalled. And the processor exits the special speculative mode once the original load miss comes back, as you can see over here. It flushes its pipeline, so it pays some penalty. Flushing the pipeline is similar to a stall, right? You're not doing useful work during that time. And then it re-executes the first load that caused entry into the run ahead mode, and that load hits. And at some point, the second miss also completes, and the processor doesn't stall for that miss either, as you can see. So of course, this is a nice case, right? So you can save a lot of cycles, as you can see. And this may happen. This is just 2 cache misses, right? You can actually parallelize 8 cache misses potentially, or more. In our experience, you've seen a lot, actually. So basically, the idea is, instead of stalling the instruction window, run ahead, speculatively pre-execute, just for the purpose of prefetching. And hopefully, you will generate some independent cache misses that you could not have generated with a small instruction window. And that would save you cycles later on. That's the idea. And this is a prefetching mechanism. This is a particular prefetching mechanism, as you can see. It's a very frugal prefetching mechanism. It uses the stall cycles to execute the main program to prefetch. And if you're executing the program, you're basically covering any program access pattern that you will see in the future. They just have to be independent of the miss that caused you entry into run ahead mode. Okay, so that's basically what I just said. These pre-execute, instead of stalling, these pre-executed loads and stores independent of these L2 miss instructions generate very accurate data prefetches. Very accurate because you're following the program path for both regular and irregular access patterns. Instructions, also you do instruction prefetching. Instructions on the predicted program path are prefetched in the instruction cache and also outer cache levels. So that's nice. You can do both instruction and data prefetching because you're really executing the program that you're going to execute in the future. And on top of this, hardware prefetcher and branch predictor tables are also trained. So you have this prefetcher. We always assume that you have another prefetcher, as you will see. And branch predictor, that's also happening, and you're training them with future requests. So there are a lot of interesting benefits over here. Okay, so let's talk about, but like with every idea, there are pros and cons. So these are, it's actually implemented in at least 3 processors. There's more potentially that we don't necessarily know of. But let's talk about the advantages of the idea of this particular prefetching. Clearly, this is a very accurate prefetcher for data and instructions to all cache levels. It follows the program path. This is true for all many thread-based prefetching methods, actually. But here we're executing the main program. We're not creating a special thread. So the overhead is very low for the programmer as well as the hardware. That thread already exists. That's the main program. It's simple to implement. Most of the hardware is already built in, basically. You're really executing the program. You're just doing it in a different way, speculatively. There's no waste of hardware context, meaning you're not executing this program somewhere else. You're executing it on the place that you're going to execute in the future, and you're executing in the past. And this actually helps utilization of the hardware resources. And also, as I said, there's no need to construct a special purpose pre-execution thread for prefetching if you're comparing to those approaches. But of course, like with any idea that you have seen in the course of this course, there are disadvantages and limitations. So one you may have seen, now you're clearly executing extra instructions. You're doing one pass over the program while otherwise you could be stalling. And then you're going to re-execute those instructions again when you come back from run ahead mode. This is a problem, actually, potentially. And we actually solved it in later works. You're limited by the branch prediction accuracy because now you actually need to go ahead, run ahead in the instruction stream. If your branch predictor mispredicts at some point, and that misprediction is dependent on a miss that you cannot resolve, you will be on the wrong program path during the speculative execution. And while this is not necessarily bad, it may not be useful. Basically, you're executing instructions that are not helping your performance. Okay, but this is actually true. Branch prediction always is limits. So in a sense, what we're doing is we're using the instruction window to get the benefits of future instructions. We're bringing future instructions to the instruction window. Whenever you increase the size of your instruction window, you'd better have a good branch predictor, right? Because you're really going further in the instruction tree. Okay, you cannot prefetch dependent cache misses, and this is a big shortcoming. So if one miss is dependent on the another, then clearly you're not able to prefetch that. Later works also try to improve it. I will mention them, but not go into detail. And then the effectiveness is also limited by memory level parallelism. You may run into this speculative mode. You may not get any cache miss. That means that you don't have enough memory level parallelism around the vicinity of that code that you're executing at that point. So run ahead may not be useful for you. And then how far ahead you can prefetch is limited by the memory latency. So basically, if your memory latency is not high enough to get to the next miss, then you will not be able to get to the next miss. So these are actually really interesting things. And these are all related issues happen in execution-based prefetchers and hardware prefetchers as well. Okay, but I wanted to give you a treatment of it because I actually spent a lot of time optimizing it. And I want to give you an example prefetcher. We'll see other example prefetchers later on that are not as capable. So strike prefetcher we've seen, for example. Strike prefetcher does A plus 4, A plus 8, A plus 6, A plus 12, A plus 16. That is specialized for a particular pattern. This is not specialized for any pattern. This is executing the program. Okay, so let's take a look at the performance of this, just to give you an idea. So these are different workload suites that we tested with Intel, and y-axis is micro operations per cycle, IPC, you can think of it that way. And there are 4 bars over here. Average is the most important part because it's average across many suites. Some of these are, for example, multimedia, web workloads, productivity workloads, server workloads, workstation workloads. It's classified that way. You can read the paper for more detail if you're interested. No prefetching is not good. If you add a prefetcher, baseline prefetcher, that's actually that actually operates based on the principles of streaming, but it's actually much more powerful, which I will not get into. You get a lot of performance. So a basic prefetcher actually buys you a lot of performance. If you don't use that prefetcher but use run ahead, you get even higher performance, as you can see. But not always. It depends on the suite over here. It depends on the workload. But if you use the prefetcher and the run ahead together, the basic prefetcher, streaming prefetcher, think of it that way, and run ahead together, you get even more performance. So run ahead improves performance by more than 20% over a baseline simple prefetcher, let's say. It's not that simple. It's still optimized heavily. So this also shows you that a hybrid prefetching mechanism does better. Okay, that's interesting. So how does this compare to a large window, which was our goal? Basically, you get the benefits of almost 3 times the size of a window. Instead of implementing a 384 entry window, you implement 128 entry window plus run ahead. And you get the benefit of almost a 384 entry window. Of course, this depends on the workload. Sometimes you get the benefit of a 1024 entry window. So it's not bad, actually, as you can see. So ideas in prefetching can actually be employed in order processors as well. So this shows that if you actually implement this sort of prefetching on an in-order processor, which we discussed early on before we introduced out-of-order execution, you get even higher benefits. Why in-order processors cannot tolerate memory latency, right? There's no instruction window. They just stall when they get a cache miss, right? So the performance improvement is actually around 40%, let's say on average, as opposed to 20%. So that's interesting. It's interesting because these results are very consistent with what other people have found in real processors after they implemented this idea. So if you're interested, this is actually the first paper I wrote in my PhD. You can look at it. There are other versions of it. But you can see that these Sun folks, Sun Microsystems folks, on other workloads, this is an in-order processor, mostly in-order processor. They have some tricks also to make it tolerate latency a little bit more. But they basically show that you get 40% better performance on their in-order processor if they use a variant of run-ahead execution that they call scout threading. So it's actually nice. Someone else in industry really validates your result that you have done without building a processor. They build the processor and they actually validate it. That's actually a very good thing when you're doing research, let's say. And if you're interested, this is Sun's paper where they explain these results and what they do. Okay, and actually there are a lot of interesting ideas in the Sun processor. Later it became Oracle. What they did in this work is they actually tolerated the latency. They actually tried to reuse some of the results that are generated during this pre-execution, but that becomes much more complex. So if you read this paper, you will see a lot more complexity over here. Okay, so later works also showed IBM, for example, Power 6 implemented, and they have actually very interesting results over here. They also implement prefetch throttling. So they have very interesting prefetching architecture that employs run-ahead execution, conventional prefetching, and prefetch throttling. If you're interested, again, you can take a look. You can see that they basically show that run-ahead execution and prefetching are synergistic with each other. I will mention Denver because we talked about Denver, if you remember, in multiple lectures, because these folks, NVIDIA, this is NVIDIA's ARM processor, and they actually implemented dynamic binary translation, for example. It's a 7-way superscalar engine. It's also mostly in order, actually. And they also implemented run-ahead execution, and their explanations are actually very nice. If you read this, for example, run-ahead complements the hard. They have a hardware prefetcher that is a striding prefetcher. Run-ahead complements the hardware prefetcher because it's better at prefetching non-strided streams. This is basically their way of saying more irregular patterns, let's say. And it trains the hardware prefetcher faster than normal execution to yield a combined benefit of some number on different workloads, right? So again, this is actually interesting. And the prefetching architecture that they have over here is, according to them, is quite powerful. They basically say these and other features, run ahead and other features, help Denver outscore or outperform an older ARM processor by more than 2.6x on a memory-intensive workload, basically. Okay, and I would recommend you take a look at these papers if you're interested. So it's actually very interesting to see the ideas in real life. So I will not talk about run-ahead enhancements a lot. I think this is also interesting because whenever you have a prefetcher, you need to optimize it, basically. That's the key. And there are some papers related to this. And let's discuss the problems, though. These problems we've already discussed, right? You have energy inefficiency. You have a large number of instructions that are speculatively executed. How do you curb that? How do you reduce that? You're ineffective for pointer-intensive applications because you cannot parallelize dependent cache misses. How do you solve that? One way of solving that is predicting the values of those dependent instructions. Actually, this works nicely. If you read that paper, there's a simple mechanism to help that. It doesn't always work, though. And then you have irresolvable branch mispredictions in run-ahead mode. How do you, because you cannot recover from a mispredicted branch that's dependent on a cache miss, right? Because you cannot correct that. As a result, you're on the wrong path in the remaining time. And there's a lot of interesting analysis on what happens on the wrong path. When a processor goes on the wrong path, can you somehow detect it? Can you somehow observe what happens and say, okay, I'm on the wrong path. I'm going to stop the execution. We discussed this actually, confidence, branch confidence estimation, for example, is an example. But there are other ideas. For example, once you start getting a lot of null pointer dereferences, you're trying to access memory address 0. That's an indication of you may be on the wrong path. Or otherwise, your program is wrong, right? Which one do you pick? I will pick wrong path, and if my program is wrong, I'm doomed anyway, right? So your processor can guess whether it's on the wrong path, basically, and that's the idea of this wrong path events, for example. Okay, so you can look at some papers that basically make run-ahead execution more efficient, and I can certainly talk more about run-ahead execution for hours, but we don't have time for it. Let me give you a perspective, though. So this work was also recently awarded the Test of Time Award. But let me give you the thinking. This is what I would like to emphasize because, again, the most important thing that I would like you to take away from this course is critical thinking. If the world is going one way, you can change that way potentially by thinking critical. So what was the world like at the time we were developing these ideas? This was early 2000s. I was a budding graduate school student. There was a huge focus on increasing the size of the instruction window. How do we increase the size of the instruction window? There are many papers written about it. And designing bigger, more complicated machines. It's happening, but basically, run-ahead introduced a different way of thinking about it. Basically, it questioned that. It basically said, instead of designing huge machines, let's keep the core very simple and efficient. And let's do something else. with that core. We give up some benefits, yes, at the expense of some benefits. For example, if you increase the size of your instruction window, you can tolerate some of the other latencies, like floating point latencies at maybe 60 cycles, etc. Yes, maybe you give up some benefits because there may be other ways of handling them actually. But let's use aggressive automatic speculative execution solely for the purpose of prefetching. Right? That's the idea. So it's really the different way of thinking that made a difference, in my opinion, and it's synergistic with prefetching and branch prediction methods. As a result, a lot of interesting and innovative ideas ensued, which we don't have time to cover. If you're interested, you can take advanced courses, of course. And but I will mention a couple of other works that inspired us. So this is actually a work that was published in 1997 that does something similar, but it doesn't go all the way. It does it on a very simple processor. It makes some design decisions that are very interesting also. But this is really the core of the idea. And then there's also this very interesting work. This is a one-page paper that was written in 1998. It basically takes a position, basically. It says, optimize for memory level parallelism, not instruction level parallelism, because memory is the bottleneck, basically. And I think this is actually a good philosophy. As you can see, these critical thinkers are really challenging the status quo. And if you're interested in a lot of ideas, this paper has a lot of ideas. If you want to work on something related, there are a lot of interesting ideas. But let's look into the future also. These are some slides that I used to basically discuss a retrospective on run ahead. So microarchitecture, especially memory, is critically important actually, and we need more of these techniques. So earlier in the break, one of your fellow students came and he basically said, "Isn't there a lot of inefficiency in the system?" Meaning, for example, even if you have a 64-bit register, you may be using only 1 or 2 bits. You may have a 90 megabyte cache, you may be using only 1 megabyte of it. In fact, we did a lot of studies, and I personally did a lot of studies actually, that showed that more than 80% of the cache space that you have is not used. There are blocks in there, yes, it's used, but those blocks are not going to be needed by the processor anytime before they're evicted. So they're dead blocks basically, more than 80%. So you have these huge caches, on average, more than 80% is not used. Basically, we need this critical thinking to enable much more efficient systems going into the future. And I think RunAhead is also a great example of harmonious industry-academia collaboration because we collaborated with Intel on this one. And maybe I should mention this. Fundamental problems will always remain fundamental. Basically, memory is there. It's not going to go away, let's say. And they will require fundamental and creative solutions. The status quo, basically, making things bigger and bigger and bigger, larger and larger and larger caches, that's an easy thing to do, right? And that's happening, clearly. But we need to somehow disrupt the system so that we get rid of this inefficiency, right? And we've already seen how inefficient it is. And this was a citation for the award. If you're interested, you can take a look at it. So maybe I'll give you some advice before we go into some prefetching algorithms. This is an example where I would recommend people to follow their passion. Because while you're doing research, and I personally experienced my several times, with processing in memory also actually, even worse in processing memory, for example, you will get people who say, okay, what is this about, right? This is not going to work. And you may get that for decades and decades and decades. But if you follow your passion, and if you have a good principles, of course, right? You're not really working on something that completely does not make sense. Of course, that does not make sense becomes interesting. How do you define it, right? Basically, you need to push forward in the presence of pressure, outside pressure, that may not be receptive to your ideas, right? You don't have to necessarily be received very well today. What matters is what you've done and what impact you've had over time, right? So I think this is very important. Since you're going into whatever area you're going in, you will also see this. Especially some folks get very ingrained in the ways of doing things, and they will say, this is the way we do things, right? And that's not necessarily a good way of doing things. That's not a good reasoning, right? This is the way we do things, but who said that it's right? The fact that you've done these things 100 years, 200 years, or 10 years doesn't mean that it's the right thing to do, right? So that's why you need to think critically and disrupt what's going on, basically. Of course, with principles, right? This requires being resilient, of course. I think this is really important because if you're not resilient, you can quickly give up. Okay, this is the way they do things. I'm going to do things that way, right? Well, then you lose the opportunity to actually do something much better, basically. And I think in the end, focusing on learning and scholarship and really rigorous way of demonstrating the benefits of what you're doing is really critical, basically. You cannot, the arguments have to be scientific and based on learning and scholarship, right? You cannot just say, okay, this is a better idea, done. That's what the naysayers are doing, basically. This is the way we do things, for example, or that's never going to work, right? Basically, you need to demonstrate in a much better way. And I think in the end, the quality of your work defines your impact. Even if you don't get that impact today, you may get it 10 years down the road. And I have personal experiences, clearly, that have shown that. RunAhead is one example. I mean, RunAhead was a bit actually lucky compared to some of the other work that we're doing. For example, RunAhead, there were folks in the industry that quickly adopted it, like people from Sun, for example, and people from IBM and people from NVIDIA. But there was also a lot of resistance. I mean, even right now, there's resistance in the sense that we're building these large instruction windows, so why do we need some other prefetching techniques? But again, that's not a great way of reasoning. These instruction windows are coming at a big cost, as we discussed. Okay, so if you want more on RunAhead execution, we have a lot of lectures, and you can also read my PhD thesis. That's a long one. And you can also look at these lectures. And this is a short one where we discuss the impact of the work. Let me give you some more recommended material on prefetching, and then we're going to cover some more prefetching ideas relatively quickly, and then we're going to be done. As I expected, we're not going to go into virtual memory today, so that's good. There are a lot of interesting things to cover in prefetching, and I'd recommend you take a look at it. So this picture, for example, I specifically picked this picture, but this picture is an example of thread-based prefetching. So you fork a thread that basically predicts a branch, for example. That prefetches your branch, or pre-executes a portion of the program that predicts your branch more accurately. You fork a thread that prefetches the load before the main program. So you have a main program and you have helper threads that help the main program. This is also a very cool idea. And we talked about RunAhead, software prefetching. And there are also address correlation-based prefetchers. So a very, very small fraction of it I will briefly talk about today, but we will not do a complete treatment. Address correlation, what does correlation mean? You have address A, B, C, and you almost always see D after that. And these have no pattern other than that. Basically, A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. If you see that, you can prefetch, potentially. But this requires you to detect the patterns, right? Linked data structures tend to be that way. So if you have a linked list, for example, that you're traversing, the individual nodes, addresses may have nothing to do with each other. They may be completely random. For example, let's take a linked list that's of 6 entries, A, B, C, D, E, F. That's 6, right? That's good. You cannot predict the first time you go through this linked list because they're completely random. But if you recognize the pattern, the next time you go through the linked list, you can prefetch the entire thing. Right? That's correlation, basically. A, B, C, D, E, F, A, B, C, D, E, F, A, B, C, F, that repeats. Of course, it's very simple, right? Now, once you go into graphs, it's not as simple because now you have a data structure that's not linear, that's really more randomized. And if you have that data structure, you can still predict potentially based on the paths you're taking in that graph, right? So you need to be a little more intelligent in terms of how you actually do that. If you're, of course, traversing completely randomly the graph, maybe you're not going to be able to prefetch that at all. And that's where potentially prefetching, pre-execution methods come in. With these random patterns are much better predicted with pre-execution based prefetching. But I just gave you an idea, the idea of address correlation-based prefetching, for example. Okay, there are a bunch of recommended readings. I will just flash these, and I will go into another example, which we've also covered, but I want to cover a couple of issues here. Even stride prefetchers are quite interesting, actually, because there are multiple ways of designing them. So I've already given you this, right? Consider that following strided memory address pattern. Stride is n in this particular case, a plus n, a plus 2n, a plus 3n, a plus 4n, dot, dot, dot. And the idea of a stride prefetcher is to record the stride between consecutive memory accesses. If the stride is stable, meaning you're kind of confident that things are not, the stride is really n, use it to predict next some number of memory accesses. And I really don't like this n repeated over here because that's not very principled, right? Let's do m. You don't want n to be overlapping with that n, right? Next, some number of memory accesses. And we've already discussed this basically. But there are two types of stride prefetchers also, right? One is, how do you determine the stride basically? You can determine the stride on a per instruction basis, meaning you have a load instruction, you just look at its access pattern. Or you can determine it on a per memory region basis. You don't care about the instruction that generates the stride. You care about the memory region and what's the stride in that region. Right? These are two different ways of doing things, and they actually lead to two different, I shouldn't say complete different, two different sets of trade-offs. And both of them are implemented in real processes, by the way. Okay, so let's take a look at instruction-based stride prefetching. Let's go into a little bit more detail how to implement. You have a load instruction with its program counter. You index into a table. You have a tag in the table to match, which gives you the last address referenced and last stride and the confidence of the stride. And if you're confident, whenever you actually see this load instruction again, you take the last address reference, add the stride to it, and generate a prefetch request. If you want to be aggressive, you keep adding the stride and generate many prefetching requests, right? That makes sense, hopefully. So this is one way of implementing a stride prefetcher. Sorry about that. That's not what I want to do. I wanted to get rid of this thing. Okay, good. Hopefully I didn't destroy something. Live stream is still going on, right? Okay, I think so. Okay, so basically, the upside of this is each load and store instruction can lead to a memory access pattern with a different stride, right? So you have and you can basically you can distinguish between different loads, and we discussed this when we discussed vector processing. If you go back to that lecture, lecture 20, I believe, where we discussed vector processing and each load having a different stride potentially. Now you can distinguish between them, but you're limited in the sense that you can detect only those strides. Timeliness can be an issue. Initiating the prefetch when the load is fetched the next time can be too late, basically. So you fetch the load, and then you initiate the prefetch as last address you've seen by this load plus the last stride. It may be too late because the load is going to access data cache very soon, right? So you really need to look ahead. In the potential solution is basically look ahead in the instruction speed. Okay, another way of designing this prefetcher is cache block address-based prefetcher or memory region-based. Basically, you have a cache block address. Based on that block address, you determine the stride. Now, I'm not going to exact details of how you do this, but this can detect strided memory access patterns that appear due to multiple instructions. You don't need a single load. You can have multiple loads. Basically, this pattern can be caused where each access in this pattern can be caused by a different instruction. And it can happen, actually. This happens in real life. Now you can detect this. You're independent of the program counter. And stream prefetching that we discussed earlier, stream buffers, is a very special case of this memory region-based stride prefetching where n is 1. You always keep going through the next block, basically. You don't care which instruction caused it. You basically keep going streaming through memory or striding through memory. So, okay, if you're interested, this is the paper that introduced the instruction-based stride prefetching. And this is a nice Intel white paper. It doesn't give you a whole lot of detail, but it kind of shows you that they have an instruction-based prefetcher into the L1 cache. And you can see how they do it, basically. Again, it's simple based on what we have discussed. And this is a memory region-based stride prefetching. That's the stream buffers, essentially. Okay, now this brings up the question, what about more complex access patterns? Simple regular patterns, stride and stream prefetchers do well. Complex regular patterns, they don't do well. For example, you may have multiple regular strides. Your strides may be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Because of the way you're dealing with data structures in a program. I may have an example later on this, but we don't have a lot of time. But this is certainly possible. You're always accessing some part of your data structure in a regular fashion, or you're jumping through the data structures in a more regular fashion. And this happens in real programs a lot. I mean, not just 1, 2, 3, but different ways. I'll show you an example in a little bit in terms of the correlation. But clearly, this is a pattern that you can detect and you can prefetch for. But it's not as simple as just looking at the last access. And there are even more irregular patterns like linked data structure traversals, like we discussed, indirect accesses, totally random accesses, multiple data structures accessed concurrently. Now your prefetcher needs to be more intelligent. So this is one example from a real program. You see the execution time, and this is the stride pattern, if you will. So you can see some regularity over here. This sequence of strides keep getting repeated because of the data structure access patterns. And it's predictable, but you need a prefetcher that can predict this. And this paper describes how to build it. So basically, the key idea is figure out, keep a history or signature or pattern of strides. I'm not going to tell you exactly how to do that. Learn and predict what stride might come next. So for example, if you see 7 minus 6, 12, the next prediction should be 6. If you see minus 6, 12, 6, next prediction should be minus 5. And there's a way of bootstrapping the predictions and looking ahead. This paper has, you don't need to know about it, but it's very interesting. I would recommend looking at papers like this. And existing systems actually have prefetchers that are as capable as this, for example, and even more. For example, we talked about the Apple M1 processor, right? It has a lot of prefetchers that are actually quite capable, at least based on the reverse engineering people have done, because Apple doesn't really volunteer information about their prefetchers, except for their patents, which you may want to look at. Now, let me give you another example, and we will conclude. Basically, another example is machine learning. I kind of said that, right? And this is a paper that we have recently written, led by Rahul. Konstantinos is also there. And the idea here is to use reinforcement learning to actually detect these patterns. And this is a very algorithmic approach to learn to take an action in a given situation to maximize a reward. So all of us are reinforcement learning agents. We examine our environment, look at the state, we take an action, and we get rewards, basically. So this is a very fundamental way of learning, very different from neural networks. Of course, you can use neural networks to do reinforcement learning. That's a different issue. But basically, this agent, based on its past experiences, stores some expected reward values for every state action pair. In a given state that resembles my current state, what action should I take to maximize my rewards? Reward can be performance, for example, right? That's the idea. So basically, this is the expected return for taking an action in a given state. And given a state, the agent selects the action that provides the highest reward, let's say. That's the Q value. There's a particular way of doing it. It's Q learning. And if you're interested in reinforcement learning, I would definitely recommend taking machine learning classes that cover reinforcement learning, in addition to neural networks. And Pythia, the idea of Pythia is to formulate prefetching as a reinforcement learning problem. You have an agent, prefetcher. You have an environment, processor, and the memory subsystem. State is the features of a memory request to address A, for example. And action is what kind of offset you should use to prefetch after this. And there's a reward that I'm not going to go into, but that basically penalizes you if you take the wrong action, let's say, if a prefetch is not used, for example. And the paper has a lot of detail on what should be the state, what should be the actions, but I kind of gave you an idea. For example, state could be the delta, the stride that you think is there, sequence of last 4 deltas, sequence of strides, and the rewards you need to use. And this is a slide I'm not going into, but basically you look up, based on the state, you look up an expected reward. If I take this action given the state, what is my performance going to be long-term into the future? And then you decide the action with the maximum reward. And you learn this over time, of course. It doesn't happen immediately. Over time, I learn. For example, I have a stove. I put my hand. If the stove state is hot, I should not put my hand over there, right? I learned that over time. Let's finish this, and then we're going to be done. But basically, over time, you learn to do better decisions this way. And as a result, your performance is best over many, many prefetchers over here. So I would recommend looking into this because, or the idea of using reinforcement learning to design controllers like this, because you can see that the performance of a reinforcement learning-based prefetcher is much better than heuristics that we have discussed so far. Okay, so this is where I'll stop. We will continue with virtual memory tomorrow. And there's a lot more in the paper.